High-quality CPR has been shown to increase survival. It only provides about 25 to 40% of normal blood flow to the heart and brain. Even when performing high-quality CPR, air can be drawn in during chest wall recoil, depleting the vacuum that is needed to fill the heart. During CPR, blood is circulated forward by two mechanisms: the cardiac pump mechanism and the thoracic pump mechanism. With the cardiac pump mechanism, direct compression of the heart between the sternum and the spine forces blood out. More importantly, the chest also becomes a thoracic pump. Chest compressions create a positive pressure that forces blood out of the heart and air out of the lungs. Compressions also cause a slight increase in intracranial pressure, which reduces cerebral perfusion. Then, during the decompression phase, the chest wall passively recoils, creating a slight negative intrathoracic pressure. This vacuum draws some blood back into the heart, pulls some air into the lungs, and fills the coronary arteries. ICP is also slightly lowered during decompression. Chest compressions create a sequence of alternating positive and negative pressures that help to circulate blood. The more blood that can be returned to the heart, called preload, the more blood that can be circulated forward on the subsequent compression. Optimizing preload is critical for maximizing the effectiveness of CPR. CPR alone does not maximize the amount of blood circulated, because just as the chest wall begins to recoil, air rushes in through the open airway and eliminates the vacuum that is needed to fill the heart. Once the negative pressure is gone, the heart stops filling. This diminished preload results in decreased cardiac output on the subsequent compression. Studies also show that caregivers often make errors during the performance of CPR that compromise its effectiveness. For example, ventilating too often or with too much tidal volume causes excessive positive intrathoracic pressure that limits blood flow back to the heart and increases ICP. Compressing too slow fails to generate enough pressure within the circulatory system. Compressing too fast limits preload because the heart does not have enough time to fill with blood. Finally, if the chest wall does not recoil completely, it results in decreased blood flow back to the heart. Given that we only get about 25 to 40% of normal blood flow with conventional CPR, it's important to get it right. Minimize interruptions. Provide proper chest compressions at a rate of 100 to 120 per minute, a depth of at least 2 inches, and allow complete chest wall recoil. Provide proper ventilations at a rate less than 12 per minute, a duration of 1 second, and with no more tidal volume than is needed to produce visible chest rise. Zoll's resuscitation platform is designed to promote high-quality, high-perfusion CPR.